This conference will now be recorded.
Okay, so today we would like to talk about the linear regression concepts. Okay, so let's talk first what exactly the um, so I think you guys are already aware of it. What is machine learning? What type of machine learning algorithms we have it, like supervised and unsupervised, right? And from that particular supervised, you may have like classification and regression, right? So from that particular thing today, uh, from the part of the regression, we are going to discussing about the a simple linear regression. Okay, so you can say that okay, it's an introduction to linear regression algorithm in a machine learning. Okay, or introduction to linear regression and machine learning algorithm. Okay, algorithm. So from this particular thing in a machine learning, okay, the linear regression is the linear regression algorithm in machine learning is a supervised technique. So supervised? What exactly the supervised? Tell me, tell me, guys. What exactly the supervised machine learning algorithm? Tell me what exactly the supervised machine learning algorithm. Hmm? See, guys, supervised machine learning algorithm or technique is mapping that a function best prediction. Okay, supervised means okay. So you may have some kind of training data. You may have some kind of a training data. So that we are calling it say supervised machine learning algorithm. Okay. So supervised machine learning algorithm means when we have some kind of training data or when we have some kind of labeled data to predict your outcome. Okay, that we are calling it say supervised machine learning algorithm. Is it clear my point? Is it clear or not?
Yes, sir.
Okay, so from this particular supervised machine learning algorithm, so there is different kind of algorithms are there, like regression based algorithms and classification based algorithms. Now we are talking about the regression based algorithm. So coming to this particular regression based algorithm, coming to this particular regression based algorithm. So regression based algorithm, so here you have the you will able to get the or you will able to get your predicted value. It can be something like a number or continuous data. Okay, so let's talk about here. Regression is the one of the supervised machine learning category or machine learning algorithm where this result is predicted using known parameters. So you may have some known data, okay, that are correlated with the output variable actually or output data. Clear? So and here, so your regression is to predict the values within the continuous range rather than the classification of or rather than to classify in a categorical thing. Okay, so here the result it should be like it's a numbers format or continuous data. Okay, the known parameters are used to make a continuous or constant slope which is used to predict unknown result. So might you don't have the you don't know what exactly your result, so you can able to predict your unknown result with help of your known parameters. Okay, with help of your known parameters we can able to predict the unknown result actually. Okay, it is try to draw the best fit line from the gathered data or number of points, okay, or several points, and it is used to predict the relationship between the dependent variable and independent variable. Guys, what exactly the dependent variable and independent variable? Tell me. Am I explained the what exactly the independent and dependent variable in the beginning classes itself? Hmm? Tell me. For example, I just want to predict the salary of the employee based on his experience. So there you have to predict your salary, or you have to predict the employee salary, right? So there the salary is the dependent variable, and the number of years of experience is, it should be the independent variable. Okay, a response variable or output variable. Okay, so you have several names are there. Okay, so for dependent variable, response variable, okay, and a target variable. So you may have different kind of names in a different type of books. Okay, so don't confuse yourself. Even dependent variable, even response variable, even output variable, even target variable, these are the four names are is the same only. Okay, so it tries to draw the best fit line from the data gathered from several points. It is also used to predict the relationship between dependent variable and independent variable. So that best fit line, it can help you to predict the exact relationship between the dependent variable and independent variable. Okay, so you can see a small example here. For example, if we have the if we have the okay, if you have to predict the speed of a car given a distance, so you have some kind of distance and the speed for it. So that is one thing, and predict the salary of the person according to the number of years of experience. So this different kind of names, a different kind of okay examples you can able to use it. That's not a big issue. That's a known thing only. Okay, and oh, just a minute, guys. Control chat. Yeah. So it is a regression problem. So let me take a small example, or else you can see this particular graph. It can help you to know what exactly this one. Okay, yeah, you can carefully observe here, guys. You just try to understood my point. See here, this is your x is the independent variable, and this is your y is the dependent variable. Okay, so when we have the two things like response variable or features variable, so you have to plot we have to plot this input variable and output variable. So you have some kind of data points, so you have to go for predict the best fit line. You have to predict the relationship between these two variables. For that one, we can able to go for using the simple linear regression algorithm. Okay, so that's what thing you should understand over here. Is there any question regarding about what I explained till now? Tell me, is there any question regarding about what I explained here?
No, sir. No, sir.
Okay. Yes. So don't you think too much regarding about these names, and the particular things are very simple. So, oh shit. Okay. Yeah. So now we'll talk about the a linear regression in a machine learning algorithm. So previously we seen that what exactly the supervised, what exactly the regression, and that's what we seen it, right? Now we will see the linear regression algorithm in a machine learning. Okay, so coming to this particular thing, so linear regression is the nothing but, so we need to go for, we might have the dependent variable and independent variables, right? So when we have the dependent variable and independent variable, so we have, you can say that it's a linear regression, or you can say that it's a least square. Basically it is the statistical method to regress the data with dependent variable having the continuous values in independent variable. Okay, so here your dependent variables are the continuous values, but when coming to the independent variables, it may be continuous or it may be categorical values. It doesn't mean that every time it should be like it should be like independent variable, it should be like continuous. Okay, but dependent variable, it should be continuous. Dependent variable, it should be continuous, but independent variable, it may be continuous or it may be categorical. That situation we can able to use the linear regression. One more time, you just read this particular line. Linear regression, it is a statistical method to regress the data in a to regress in the sense we have to predict, you have to predict, okay, your dependent variables having the continuous values, whereas the independent variables, it may have the continuous, it may have the categorical. Okay, so the word, in other word, linear regression, in another words, linear regression is a method to predict the dependent variable based on the independent variable. Okay, based on the independent variable. It can be used, okay, so it can be used for the cases where we want to predict some continuous quantity. Whenever you want to predict some kind of continuous quantity data, when you want to predict some continuous quantity data, that particular situation, this is the linear regression we would like to use it. Okay, we would like to use it. This is what a linear regression, it's an introduction. Okay, now here we need to understand there are two type of relationships are there. One is the not deterministic, and second one is the deterministic. Okay, so let's talk about those particular relationships now. The relationship between the two variable, it should be a deterministic, which means if one variable can be accurately expressed by the another one actually. Okay, so degree degree Celsius and Fahrenheit, that's the example for the deterministic relationship. And the statistical relationship is not accurate in a determining the relationship between the two variables, that we are calling it say okay, and that we are calling it say not deterministic. See guys, wherever we go, okay, if we have some kind of Celsius, if you want to be converting into the Fahrenheit, so it should be easy, right? It won't be changed for place to place, right? It can be same, whatever the Celsius that we can able to representing in a Fahrenheit, so that we are calling it say deterministic, for example. And this, sometimes we see one person height, it's if even some person height is will be very high, but the weight will be very less. Sometimes the height will be very high, the weight will be very high. Okay, sometimes it can be medium, right? Yes or no? So but sometimes height will be very less but the weight will be very high. So lot of situations are there, so there you can't able to give the relationship and accurately with height and weight, then that we are calling it say not deterministic. Okay, is it clear my point? I said, is there any question regarding about these 2 points? Guys, are you following my points or not?
Yes, sir.
If not, please let me know.
Okay.
The core idea is to obtain the line that best fit the data. The best fit line is one of which total prediction error, all data points are as small as well as possible, as small as possible. The error is the distance between the points of regression line. Okay, so here what we will do, our main motto is you have to be reduce your error. Okay, you have to reduce your errors. So that is your main thing. Errors is the nothing but the distance between the your points and a regression line. Let me take a small graph for the understanding of the thing. Okay, for example, this is my x data and this is my y data. Okay, for each and everything you have some kind of y values, right? So you have the some best fit line. By the time this is your regression line, so from this particular line we have to find the distance between the each and every point, so that we can call it's an error. Okay, when you sum up this all, you have to get the error is very small, that we should decrease it. Even sometimes you can take the line something like this, right? But if the errors are very high, if the sum of errors of all points with this regression line with this points, if it is a high, then we won't consider this particular point. So ultimately you have to figure out the whatever the best fit line which is giving the very minimal error thing. Okay, clear? Clear, right? So you just read one more time. The core idea is to obtain a line that best fit the data. The best fit line is one of for each total prediction errors or all data points or as small as possible actually. So error is the distance between your data points and regression line only. In a simple linear regression line, it is approach for predicting the quantitative response using a single feature and single input variable and a dependent variable, right? One input variable and one output variable. Only we do have only two things. So it is a following equation. The equation is y equal to beta naught plus beta 1 into x. Here x is my input variable or feature variable. You can have the names for the x. It can be feature variable or it can be input variable. It can be something like a independent variable. You may have different names, guys. Independent variable, input variable, and the response variable. Okay, everything will be like it's the same only. When coming to the y, y can be the response variable, or y can be the dependent variable, or y can be the output variable. Okay, so this is the equation we are calling it a linear regression equation. Okay, so here beta naught and beta 1 are the your model coefficients. So our main motto is we have to predict, you have to find out the beta and the beta naught value and beta 1 values. Whenever you know this particular beta naught and beta 1 values, that means you can able to find out your best fit line. Okay, when we have the best model coefficients, then that is the best fit line. Okay, is it clear? So for example, so this is my x and this is my y. So here beta 1 is nothing but it's an intercept. It's an intercept. For example, when my x value is a 0, then what will be my y value? That is the my coefficient, my intercept. So here my x value is the 0. At x what will be my y? That's we are calling it say your intercept. Okay, that's your intercept. Coming to this beta 1, so the minimal change in x, okay, when you change the 1 unit in x, what will be the change in y? That we are calculated with beta naught, that we can say that it's a slope. You can call it's a slope or else it's an slope, or it's like your beta 1 value, beta 1, or else you can say that it's a m. Usually y equal to mx plus c format. Here m is nothing but it's a beta 1 and c is nothing but it's a p0. Okay, intercept and a coefficient. You can say that say beta 1 is a multiplier, okay, or unit change in x. What will be the change in y that we can representing with a slope. Okay, these are the your names in linear regression equation. Is it clear, or any other question is there regarding about this one? Tell me, guys. So you can see this particular graph. Okay, so y equal to beta naught plus b1 into x, right? Your x is your independent variable, y is your dependent variable. So the minimal, the x value, when the x value is 0, what will be my y? That we are representing with the beta naught, and beta 1 is nothing but your coefficient value. Okay, so let's talk about the explanation of the model coefficient. I think I already explained in my verbals. And so beta 1 is the intercept. If the model does not include x equals 0, that means predicted value is meaningless. So blah blah of information is there, but that is not a big issue. I'm just removing this entire information because of so that's a thing you already aware of it. This will be the confusion thing, so I just want to remove it. Okay, so here beta 1 is the intercept. So that's what this particular explanation. So this is the point we can representing that it's a your intercept value. When coming to the beta 1, that's your slope value. So that I already explained it. You just gone through it once. Okay, so if the beta 1 value, it might be greater than 0, then the relationship is the positive relationship. When this particular slope will be the negative, then it should be negative relationship. Okay, so this is the relationship will be deciding by this particular coefficient only. Okay, so now how you might able to calculate this particular model coefficients. So when you are go for calculating this particular model coefficients, so here, so this is the beta naught. So this is the beta naught. It can able to calculate it the mean minus beta 1 into mean of x. So here x is nothing but it's a mean of x. X bar is nothing but it's a mean of x. Okay. So this is mean of x. So when coming to the y bar is nothing but it's a mean of y. Okay, so but you have to calculate it your beta naught 1, right? Sorry, b1, right? b1 in the sense sum of x minus x mean into y minus y mean by sum of squares of x minus x bar. Okay, sum of squares of x minus x bar. So this is the formula for the to calculate your beta naught value. So you might be thinking, how should I calculate this one, right? For example, you have the data is 1, 2 and 3, it's a 4. Okay, yeah. So this is your x data. Let us consider this is your x data, and I have to calculate the mean for it. So 1 plus 2 plus 3 plus 4 by 4, it should be how much, guys? 4 plus 2, 6, 10. 10 by 4, right? 2 2 just 2 5 just, it's a 2.5. So my mean value is 2.5, right? So now I have to do the sum of, formula is sum of x bar minus into y minus y bar. Okay, so by sum of x minus x bar whole square, right? So this is my formula. Okay, so x means each and every data point. So 1 minus x bar means, what is the x bar? It's a 2.5, right? So x 1 minus 2.5 into, what is my y value? Maybe the corresponding y also you have some data, right? So we have to calculate the y bar, and that y minus corresponding mean value. So the mean is constant, but y can be changed for every time, for every iteration. But when coming to this one, x will be changes, but x bar will be, it's a 2.5 only. When you are subtracted, when you are evaluated this particular expression with this particular data, you might be getting this particular equation, you might be getting this particular value. Okay, so this is the value. With help of this value, you can able to go for calculated your coefficient constant also. You can able to calculate it constant also. Okay, so if you know the beta naught value and beta values, then we can able to easily predict the, we can able to easily calculate the your predicted line. Okay, you can able to easily calculate your regression line. So this is the formulas you should remember it when you are working in the linear regression. Okay, so now let's talk. Here we have some kind of learning model coefficient, or estimating the model coefficient. Generally speaking, coefficients are estimated using the least square criterion, which means we find the line mathematically which minimize the some squared residuals with some squared errors actually. Okay, so here we have some kind of parameters are there, or we have some kind of matrix evaluation points are there. Okay, or else methods also there. So with help of those particular methods, we can able to figure out the best fit line. Okay, so we can read one more time. Generally speaking, coefficients are estimating the least square values, which means we find the line mathematically which minimizing the sum of square residual. That means we should be able to go for reduce the errors, right? When we are having the linear regression line, while doing the linear regression, our objective is to fit the line through the distribution which is the nearest most of the points, which is reducing the distance of the data points. That is our main motto. Is it right or not? When I'm talking the first time, so we should able to go for minimizing the distance between the your best fit line and your data points. That is our main motto. Okay, for example, for that one we have some kind of evolution of algorithms are there. So the first algorithm is, let's say, MAE. MAE means mean absolute error. So mean absolute error in the sense, we should able to go for find out the mean. We should able to go for it robust against the outlier. Using the previous example, the resultant of would be something like, okay, that's we will talk in a, okay. So mean square error. So I will explain each and everything, don't worry. So second one is MSE, in the sense mean square error. It tends to amplify the impact of the outliers on the model accuracy. For example, your y value, actual y is 10 and predicted value is the 30. The residual value, it should be like, it's a 30 minus 10 square that will be the 400. Okay, but the same thing, if I go with absolute error, if I go with mean absolute error, so MAE, so that means y minus y predicted. Okay, so it can be anything. So you should have the thing is, let's say this is the absolute meaning. Absolute in the sense you won't get any kind of negative numbers. You have only positive numbers. It can be 30 minus 10 or 10 minus 30. Both will be the same only. You will be getting the 20, right? So this is what mean absolute error and mean square error. Now we have one more evaluation algorithm to predict the or to find out the best fit line, that is RMSE. RMS in the sense root mean square error. Okay, it is interpreted how far average residuals is some 0. Okay, it is nullify square effect some MSC, the square root providing the original. See, when we are applying the mean square error, so there you are getting the very high values. Okay, but when we go through the mean square error, we can able to reduce that particular values. Okay, that is the meaning of the root mean square error. So this is the same thing. Mean square error and the absolute root mean square error both are same only, but thing is that we are applying the root for it. That's it. Other than that, that will be the same for it. Okay, and so that is a MSE and root mean square error, and we have R square. So this is the R square is very important when you gone through this particular regression algorithms. Okay, okay, so now, so this is the R square. The R square is the formula is SSR by SST. SSR means explained variation by the total variation. SST in the sense total variation. Explained variation in the sense, let's try to understand what exactly the explained variation and unexplained variation, so that you should understand, and total variation you have to understood. Otherwise R square will be little tough for it. Okay, with help of the R square only we can able to calculate it, we can able to predict, we can able to say that the model is good or bad. Okay, the best fit line we can able to determine with help of this particular R square value. So coming to this particular one, you have the this is your best fit line. Okay, and this is your best fit line, this is your y values, right? This is your y values, this is your x, and this is your y, and so you have some points are there here, so we have to calculate the mean of it. Okay, so this is the best fit line and this mean value. So for example, this is my mean value. Okay, this is my mean value. Okay, so this is the line which is my mean value. We have to find out the distance between this particular line and your best fit line. Okay, so that we should difference between your best fit line and your mean line, so you will able to get some kind of value, so we need to sum of it, so that is your explained variance. Okay, variation. And when coming to the unexplained variation in the sense, this best fit line, we have to find out the distance between the each and every point of your original data. So that is we are calling it say unexplained variation, and total variation in the sense sum of the both the things we are calling it say. So total variation is about regression line sum of a square root of the distance between the y values and ordered pair of mean of them. Okay, so y minus y mean whole square, that is your total variation in the sense. So this is each and every point. So this is the point, right? Each and every data point, and here we have the mean line that we have to calculate at the distance between them. So guys, you don't confuse about here. I just explain one more time regarding about explained variation and unexplained variation and total variation. Okay, consider this is my x, and this is my y. Okay, and these are my values. These are my values. Okay, by the time, so this all values of this data points, we have to calculate the mean. So that mean it can be the constant, so that it is gone through only one line. This is my mean bar. Okay, this is my mean of y. How can you calculate it? The mean sum of data points by the total number of data points only, right? So this is my mean bar. So here this data point, the original y value minus this mean difference is the error, and each and every error we calculated, and we can do the square. We can do the square. We can calculate the data point minus the mean square. Then after we have to sum for the next y value and your mean value, next y value and mean value, next y value and mean value. So you have to calculate the distance. Then after you have to apply the square. Then after you have to find the sum of each and everything. So that is your variation, total variation. Okay, the difference between your data point with mean of y, that we are calling it, say, total variation. And coming to the explained variation, same data points, you have same data points. This is the same data points, right? These are my same data point. This is my x and this is my corresponding y. So these are my same data points. By the time I calculated the best fit line, previous line is, it's your mean line, guys. This is your mean line. Now you have your predicted line. This is your y hat. Okay, this is your y mean of y. This is your y hat. It's a predicted line. So now you have to find out the difference between the this best fit line with your data points, the relation, the distance between the best fit line with the data points and the square of them and sum of them, that we are calling it, say, unexplained data points, unexplained variation. Explained variation in the sense, for this one, this is my mean value, right? Consider this is my mean value. So we have to find out the distance between this mean versus y predictor value. The distance between your y predicted line and y mean. So that difference between those two things, and we have to do the sum, and then we have to do the square. Then that's a explained variation. Okay, difference between the predicted and the mean, that is explained variation. Difference between the difference between the predicted and original data point, that we are calling it an explained variation. And total variation in the sense, difference between the data points minus the mean. Okay, that we are calling it a total variation. So now here explained variation by the total variation, with help of that formula we can calculate the r square. Okay, we can calculate the r square. So here you might be getting the r square value is in between the 0 to 1 only. Okay, if r square of 0 means the independent variable cannot be predicted from the dependent variable, it cannot be predicted from the independent variable. So in case of the values are, my r square value becomes 0, which means the model is not at all good. Okay, if my r square 1 indicating that the variable can be predicted without any error, so your r square is 1, that means your model is 100% good, there is no errors at all. Okay, if the value of the r square is, it's 0.912, that suggesting that 91.2% of the variation in the y can be explained with the help of the given exploratory variable, that model. In order to explain proportion variance independent variable explained by the independent, that's the thing, we don't need to worry about. Okay. Okay, so that's a simple thing, guys. Okay, RSS, TSS, total sum squares, residual sum squares, ESS, explained sum squares. So you have to understand what exactly those things. Okay, so this is exactly the theoretical part of your simple linear regression, guys. Okay, this is about theoretical information about your simple linear regression. And the tomorrow's class will you can able to go for apply this kind of algorithm. You just to go for apply the algorithm on any one of the data set, and we will see the this particular simple linear regression. Okay, clear? So tomorrow we'll see the small example or the small data set we will consider and we'll apply and simple linear regression, and we'll see the results in a in a coding wise instead of the theoretical thing. Okay, bye guys, see you.